In this video, we're going to look at how we can analyze mechanical energies using energy interaction diagrams. Let's do the example of the golf ball that we saw in an earlier video. We're interested in how the energy systems of the golf ball changes as it falls from its maximum height to the floor. As we've discussed, there are two energy systems at play here: the gravitational potential energy that the golf ball has and the kinetic energy that the golf ball has because it's moving. This means we need two bubbles in our energy interaction diagram. How do we know that these energy systems are changing? Just as with the thermal and bond energy systems, we need an indicator that tells us when these energy systems are changing. For gravitational potential energy, the indicator is the height of the object above a particular surface, in this case, the ground. We know that the gravitational potential energy of the golf ball is decreasing because the distance between it and the ground is also decreasing. What about the kinetic energy? Kinetic energy is just energy that an object has because it's moving. It probably comes as no surprise then that the indicator of kinetic energy is speed. As the golf ball falls, its speed is increasing, so we know that its kinetic energy must be increasing as well. What about the initial and final values for these indicators? Well, I didn't measure how high I held the golf ball above the ground. Let's just take that to be some initial height. The final height is when the ball reaches the ground. We're going to call that 0. For the speed of the ball, it's the exact opposite. Initially, the ball is not moving. It has no speed and no kinetic energy. It has some final speed when it hits the ground. We'll just call that V final. These are the only two energy systems in this example. We can think of this system as being closed. There's no obvious reason why we should expect that energy should be entering or leaving the system. There is, however, one thing missing in this diagram, besides the statement of conservation of energy. It's important to keep in mind that gravitational potential energy only exists between two objects. One object on its own cannot have gravitational potential energy. Therefore, part of our physical system in this example is actually the Earth itself. It's providing the gravitational force that causes the golf ball to have gravitational potential energy. We indicate this by including the Earth in our potential energy bubble. The last thing we need is a statement of energy conservation. We write this down in the same way that we wrote down the energy conservation equations for thermal and bond energies. We add up the changes in the individual energy systems and set them equal to the heat entering the system plus the work being done on or by the system. Because this is a closed system, there is no heat entering or leaving, and there's no work being done. So this is just equal to 0. Just as before, we need to be able to expand these terms if we want to calculate anything interesting. It turns out that the gravitational potential energy that an object has is just equal to its mass times the acceleration of gravity times its height. The mass and the acceleration of gravity is not changing as the ball moves. So the gravitational potential energy term can be written like this, where delta H is just the change in height of the ball. Next, let's consider kinetic energy. Kinetic energy turns out to be equal to 1/2 times the mass of the object times its speed squared. As in the potential energy case, the mass is not changing, so we can write the change in kinetic energy like this. let's now rewrite this by using the definition of a change. Change is just the final value of something minus its initial value. If we had numbers, we could then plug in values here to determine, for example, the final speed of the ball. One thing to note when you're doing kinetic energy, when you're doing this delta V squared, it is important that you square the speeds before you take the difference. Delta V squared is not the final speed minus the initial speed, then squared. It's the final speed squared minus the initial speed squared, as indicated here. Now let's think about the coffee filter. Remember, the coffee filter was a little bit different from the golf ball. Unlike the golf ball, which sped up as it fell, the coffee filter only sped up for about a second or so, and then traveled at a constant speed. For the purposes of this example, we're just going to analyze the motion of the coffee filter after that first second of fall. What makes this interesting is that because the speed of the coffee filter is not changing during this time, the kinetic energy of the coffee filter isn't changing either. However, the gravitational potential energy is changing, just as the gravitational potential energy of the golf ball changed as it fell. Now we have a dilemma. The potential energy of the coffee filter is decreasing, but the kinetic energy is not increasing. Hopefully by now you figured out that the reason the coffee filter does not speed up after the first second is because of air resistance. The resistance of the air is trying to prevent the coffee filter from falling down. It's not able to completely succeed, but it is able to completely cancel out the gravitational force, such that after a certain amount of time, the coffee filter no longer speeds up. There are two ways to account for this air resistance. The first is to just say that the energy is leaving the coffee filter in the form of heat. If you were able to measure the temperature of the air as the coffee filter fell through it, you would actually measure that the temperature increases ever so slightly. This is far too small of an effect for us to actually be able to measure it here, but it does actually happen. So one way we could complete this energy interaction diagram is the following. This is correct, but there's another way to complete this energy interaction diagram that is also correct. That is, let's consider the thermal energy of the coffee filter and the air in our system. If we do that, instead of saying that energy is leaving the system in the form of heat, we can say that the potential energy is turning into thermal energy as the coffee filter falls. Including that in our energy interaction diagram looks like this. This is an equally good way of analyzing this scenario. Note, we now have a closed system where the two energy systems that are changing are the gravitational potential energy and the thermal potential energy. I haven't written down an initial and final temperature because the change is so small that it could barely be measured. However, this makes it more clear that the energy is not disappearing, it's just being transferred into another form. While we have introduced internal energies and mechanical energies separately, there is no reason they can't work together. In this case, the gravitational potential energy is turning into thermal energy. We'll see examples in the future of how we can include even more energy systems in our diagrams to analyze more complex situations.